Okay, good morning, ladies and gentlemen. Here we're coming around. We're going to be finishing up our chapter 5 here pretty soon. 5.4c, sketching area functions. Now, we have found area functions using the fundamental theorem. And now we're going to learn how to sketch an area function. Notice my area function here is a function defined as an integral, okay? So what we're going to be doing is this is going to be an exercise on our function a of x right here. Our function a of x is going to be an area accumulator for us, okay? And we're going to be given our little f of t. Here's our little f of t, which this is our little f of t in here as well, okay? And why are we going to be doing this? Well, we're going to be doing this because what you're going to run into on the AP test is they are going to define a function as an integral with a graph. And they're not going to tell you anything about the function, okay? But they're going to ask questions about the function of which you need to know the connections on how we answer, like find h of 1, find h prime of 4. We're going to be coming through here, and we're going to be answering all these questions tomorrow, and we're going to connect all of our graphing of our area functions or our sketching of an area function. And we're going to make the connections for here, okay? So what we're going to be doing here also, this is my little f of t. Please understand here, the domain of f of t is all real numbers. Please do not confuse this a and this b on here with a and b on the area function. Please do not confuse them. They are two completely different things, okay? The domain of my little f right over here, the domain is actually all real numbers, but the thing is we are only going to be talking about a little piece of it to graph our area function rather than graphing the entire thing, okay? And if you notice, this is going to be on your worksheet M41. We're not going to be doing all of these problems. I'm actually just going to do 3 of them. In the M41 packet, it's in your pink packet there. And just before you get to that, there is a what should I be able to do worksheet, which I'm not going to say is homework. I will make an answer key for that. But as of right now, 5.4 with what we've learned thus far, you should be able to do all 5 of these problems pretty simply without today's lesson, okay? And this M41 worksheet is not, I repeat, not going to be homework, so I'm going to be kind of curious to find out how many people turn it in, which just reflects they didn't watch this video. But it's not going to be homework. We're just going to do 3 of these problems. You're welcome to do more of them after you know how to cruise along here. So again, this is an exercise on our area function, a of x, being an area accumulator. So come along for the ride here, and let's build one. So these are my rules right over here. These rules are actually on the M41 sheet. We're not going to do all these, but we're going to follow them all for the first one. So what we're going to do is we are going to sketch f of t on the given interval. Well, here's f of t, so we're going to sketch that little guy. Basically, that means I can see it's a line, so I can graph it really fine, and I can put my y-intercept, and I see I have a slope of 1 coming down my line. And if I'm at -3, well, heck, I put -3 in there while I'm down here at -1, slope of 1 coming out. And what I'm doing is I am graphing my f of t function, which is a line, but we're only going to look at it at that little chunk here, okay? And so we're going to, that's what we're doing. Okay. Using your graph of f, sketch the graph of a on the same interval. That's why I have another graph below it here. Okay. Note the y value of a point, xy, on function a represents the quote-unquote area in the graph of f from t equals, in this case, -1 to t equals x. So this bottom number is a very important number, okay? Hopefully you remember if I'm going to integrate this from -1 to x, that's going to give me a function a of x And that -1 actually gives me my C value, which reflects the particular solution that we would be talking about, okay? So how are we going to do this? How do we sketch? How to sketch A of x? Well, how are we going to sketch? Well, the first and foremost thing we're going to do is we are going to look at that bottom line. And this bottom line here at x equals 1, what I like to do is I like to draw actually a vertical line in there. And I'm going to make that little bugger red, a little bit thicker, and I do want him red. And so I'm going to draw that here at -1. And this is going to be, technically, I'm going to call this my area accumulator line, okay? And I'm going to write that down here. This is going to be my area accumulator line. This is where the basis of everything is going to happen for me. So when I'm doing my area accumulator line, I'm going to do most of these in green now. We are going to start with the bottom number. Okay, now when I'm starting with the bottom number here, I'm really confused. I don't know what's going on. I understand that. We are going to find A of -1. And we're going to find A of -1 by taking the integral from -1 to -1 of f of t dt. And what is my integral from -1 to 1? Well, it's 0. And as I'm moving along over here, I'm going to be putting in an x, and I'm going to be finding a value for A of x. So if I put -1 in, we just figured out we got 0. That's kind of my starting point. So -1, 0 is what I have down here. So the next thing, now I'm going to go to the right, too. I'm going to go right. Okay, and I'm going to pick points, except I'm going to be sensible about this. I'm going to pick integer values, meaning, I don't need any of that stuff up there. So meaning, well, if I just use -1, I might as well find out what the heck A of 0 is. Well, A of 0 is going to be the integral from -1 to 0 of f of t dt. So what is that? Well, the integral from -1 to 0 is this accumulated area underneath my curve in the x-axis. And I can make this hard right now, but I don't want to make this hard. I can count how much area is there because I got 1 square and a half a square. So this should be 1.5. So 1.5. So then I'm going to graph 0, 1.5-ish, and I'm going to put that little bugger as best I can. And then what's the next one I'm going to do? Well, obviously, I'm going to find A of 1. Well, that's my integral from -1 to 1 of f of t dt. Now, please understand, this is going to be my total accumulated area from 0 to 1. And the easiest way to think about this is I'm just going to add the pink area I have here to the green area I had. So I'm going to add 1, 2.5 more. So the area from A of 1 is actually going to be my 1.5 plus that extra 2.5. So when I plug a 1 in, I'm going to get a 4 out. So then I can come over and I can say 1, 1, 2, 3, 4. Or the other thing I could do is I can go from right here, my other one, I can move over 1 to the right, and then I can go up that extra 2.5 that I just accumulated from that curve, okay, or from that point. Now I'm still going to find A of 2 because we are going on our interval from -3 to 2, so I still have to find A of 2. Well, that's going to be my integral from -1 to 2 of f of t dt. Well, check it out. That's going to be my area of 4 plus how much more am I adding there over here when I get to 2? Because remember, this is 0. So when I'm 2, I'm 1, 2, 3.5 more. I can add 3.5 more plus 3.5. Hey, that's going to make this guy 2, 7.5, which is going to come over 2, or I can go over 3 from my previous point. and then I can go up another 1, 2, 3.5 to get me right up there. And now as we're going along, okay, what you really want to think about and you really want to focus is, what the heck is a of x? Now, a of x is an antiderivative of f of t. And if f of t is a line, the antiderivative of a line would be a what? A parabola. So as you can see, these points I plotted here, they are not going to connect in a line, but you can actually see that they are connecting in an upwards increasing, and you can see the concavity of it too. Notice, as I'm accumulating area across the point, not only is f of t increasing, the area I'm accumulating is increasing. Okay, so I'm increasing at an increasing rate, which is going to mean I am concave up. Think of the tangent lines on my original big f of t if I did that, and concave up. So I would be increasing at an increasing rate. Well, the other thing, well, now I got to go, well, I got to my endpoint of 2. Now I need to find out a couple more. Now that I went right all the way, now 3, now I'm going to go left. And now remember, when we go left, crazy things are happening. So now I want to find what is a of, well, we started at -1. What's a of -2? Well, that's going to be the integral from -1 to -2 of f of t dt. So what's happening here? Now remember, I'm accumulating area to the left. Okay, so now I need to look at this. Well, how much area am I accumulating? Well, that's a half. But remember, okay, these guys, as I'm going left, these guys are positive. My y values are positive, but because I'm accumulating to the left, my delta x, or my dt, is going to be negative. So this is going to give me a negative 0.5, okay? And that's from my 0 line. So now I got to go down at -2. I'm going to go -0.5. I went down a little bit. So I'm going to go over, and I'm going to be down right about here. And we need one more. We still need our a of -3. Well, that's going to be the integral from -1 to -3 of f of t dt. Well, now remember, when we did that cosine or that sine function, when we were integrating to the right, to the left, well, what do you notice about this stuff down here? What do you notice? Well, I can see that area as a half, but is that a positive half or a negative half? Well, think about this. I'm accumulating to the left. So in the end, all my y values here are negative because they're below the x-axis. My delta x is also negative because I'm accumulated, so that's a positive, a half. So I got to take the area I had before of my -1/2 plus a half, and I'm going to get 0. Okay, so I get -3, 0 to get to that last point, and I am going to get this little guy. Well, boy, that sure does look like a parabola. And earlier in the year when we were doing graphs, remember, what did this little point, I'm going to use a different color here, what did this point represent? If that's my derivative, my x-intercept of f of little f of t, so that's an it's not anti, but it's the derivative of a of x. So this is really f prime of t is what I'm looking at. It's really f prime of x. What are you talking about? Well, a of x is actually going to equal big F of x, isn't it? Which means a prime of x, the derivative, is going to equal little f of x. So what am I thinking about there? Well, I'm thinking about, if this is little f, this is the graph of a prime, so it's a derivative. What happens with that derivative? Oh yeah, that was a 0 slope for me. And if I look, I can see that that would have been the vertex of my parabola. Now, obviously, it's going to continue on that way, and it's going to continue on that way. It's going to go up. But we are just looking at this little piece of it, okay? So Then we're going to verify our sketch in part B above by graphing y equals the integral. We're going to graph, because our calculator is really fast, really smart. So we're going to do, crap, I can't do it that way. I got to get my template here to graph. I need my integral. And we are going to go, what's our integral from? -1 tab to x tab of t plus 2 dt, right? We can graph that. Well, hey, there's the whole graph we were looking at. Well, our calculator will do even a little bit better than this. So if I came back here, I can come, once I get to the outside of my dt, see if I come back, you see how the line gets short. So now I'm in the dt yet, so if I go over, I can actually do a control equals, and I can use my such that bar, and such that, we're going to say, we want to go from -3 is less than or equal to x, which is less than or equal to 2, and what it's going to do, it's pretty sweet. It's going to graph my derivative on the interval that I want it to graph, and I'm going to put it underneath here. Obviously, we can see, hey, yeah, we got that, and that's exactly what we did. So our calculator will integrate it for us. We know how to integrate it as well, okay? And what are you talking about? Well, we'd be able to find a particular solution if we had to, because we could take our integral from -1 to x of t plus 2 dt, couldn't we? And we could integrate this, and we could say, oh, this is 1/2 t squared plus 2t, plus 2t, and we can evaluate that from -1 to x. Well, that's going to give me what? 1/2 x squared plus 2x. That's my upper limit minus, that's going to put a -1 in there. That's going to give me 1/2 minus 2. That's going to give me 1/2 x plus 2x minus -1 and 1/2, or 1/2 x squared, forgot my squared, plus 2x plus 3/2. Hey, that's what my area function actually is. Okay? And we're going to be making some connections about this area function. And there's some things that we did earlier in the year. What are you talking about? Well, here's what I'm talking about. So let's do a minor summary that we got going on here. What? Minor summary, what are you talking about? Well, we know a of x equals the integral from -1 to x of f of t dt, correct? So we know a prime of x equals little f with x in it, correct? So the derivative of our area function is little f with x in it. It's right there, the derivative of my area function, okay? And what does that mean? Okay, well, if here's my a prime up here, I'm kind of zippity-doo on a lot. How do I want to do this? I'm going to pause, I'm going to cut that. Notice a prime is increasing because it's going up and to the right, correct? Well, what does that mean? Well, that means if a prime or f, little f of x, is positive, what did that mean for a of x, the antiderivative of my area function? A of x is increasing. Do you recall that when we did that? Okay, because all of my derivatives here, okay, it's all positive. So all the way here from -1 all the way out, my function should be increasing, and I can see my a of x is increasing. Why? Because its derivative is positive, okay? And there's all kinds of other connections that are coming in here. What's another one that I want that we're going to be getting along? Well,
The other one is if a prime of x or little f with an x in it is negative, well, what the heck did that mean? That meant a is decreasing, didn't it? Well, let's check this out.
Well, where are we at here? Well, here we're negative, right? A prime is negative. That meant A was decreasing on that last little niblet there, okay? Well, what if A prime, now think about this, what if A prime or F is increasing? What did that mean? Well, if A prime or F was increasing, okay, what did that mean about its tangent line? And I can see this, okay, is A prime is increasing. So what's the slope of A prime? The slope's 1 everywhere on that. More importantly, it's positive. Excuse me, it's positive 1. Okay? So if it's positive, A double prime or F prime is greater than 0. Okay? So if it's increasing, that meant my second derivative or F prime was greater than 0, which meant because that second derivative was greater than 0, that meant A is concave up, right? Didn't it? And check this out. Check this out. From right here all the way across, I'm increasing and positive, which meant A was concave up. Over here, I'm negative, but increasing, okay, but because I'm negative now, but positive, I'm still concave up. Still concave up. I'm increasing, therefore this function increases. It has nothing to do with the value of the derivative. If A prime is increasing, the derivative of A prime is positive everywhere. That means I'm concave up, okay? So what we're going to do is we're going to try another one here. We're going to skip that one, and we're just going to go to number 5 on the sheet, and we're going to write an integral value accumulated from where? 0 to t equals x is what we're going to do. We're not going to follow all of the rules that we just did in here. We're going to just kind of make these happen a little bit, just graph them. So the first thing we need to do is we need to graph f of t. Well, I can think of this the long way or the hard way. I can think of this is just a line with a positive y-intercept at 2, a slope of -1. So I'm going to make my dots coming down, and I'm going to graph it on this interval. And I'm going to make a table of values over here to find my a of x function. And remember, we are going to start at our area accumulator line, which is going to be 0. This is going to be my area accumulator line, so that's my starting point. My starting point is always going to give me my particular solution. So I know a of 0 is going to be the integral from 0 to 0 of f of t dt, which means when I put a 0 in, I get a 0 out, which means here's my a of x. I got to get my calibration just a little bit better. And after I find my starting point, remember this is a really important value. That's always where I'm going to start. This value has to be within that interval that we're talking about, and it is. And then from there, I'm going to go right. You can go right, you can go left, you can go whatever direction you want. But what I'm going to do is I'm going to find a of 1, I'm going to find a of 2, a of 3, and I'm going to find a of 4. Okay? And I'm going to find them all the same way as area accumulators. So this is going to be the integral from 1 to 0 of f of t
dt, except my dyslexia just got me there again. Remember, 0 is my bottom, 0 to 1. So I am accumulating this area right here, which is 1.5. So this is going to be a 1.5. So my area function is going to be at 1, 1.5. So I'm going to come over 1, and I'm going to go up 1.5. And then the next thing I'm going to do is my integral from 0 to 2 of f of t dt. And I can do this however I want, meaning I can take my 1.5 from before and I can add the, I'm increasing at a decreasing rate now. So now I'm only going to add 0.5. So this is going to come up here at 2, 2, I think even. That's kind of weird. Now check it out. I'm increasing. I'm still accumulating positive area there from 1 to 2, but the area I'm accumulating is decreasing, which means, what does that mean? I'm accumulating positive area at a decreasing rate. Concave down, maybe. Can you see it? Hopefully you can. And then I'm going to take 0 to 3 of my f of t dt, and I'm going to take the 2 I had before, and now I'm going to add the, check it out. Is that positive or negative? Well, I'm going to think about this. My heights are negative. My delta x is moving right, so that's positive. So I got to add a negative 0.5 to that. So at 3, I'm going to be back to 1.5. Oh, at 3, I'm back down here at 1.5. And then, how about 0 to 4 of f of t dt? Well, now I'm going to take that 1.5 that I was at plus, well, now I got to accumulate another negative 1.5 to get me to 0. So 4, 0. Hopefully you expected that. 4, 0. I don't know. Maybe you didn't expect that. But I did, because I saw my vertex of my parabola here, and I see symmetry about that vertex. And which way? I still got to go left, don't I? Now I'm going to go a little left. So which ones do I need to find yet? How far over do I need to go on this one? I just got to go to -1. I just got to accumulate area -1. So now I'm going from 0, -1 of f of t dt. And now I'm just going to the left of my accumulator line. So what I had before is 0, so I'm starting there. And now I'm going left, and that's 1, 2.5, and that's a 2.5. It looks like it's positive, but remember, my heights are positive, but I'm going left, so that's negative. And we knew it had to be going down, so I'm going to say -1 to -2.5. And we can make -1 to -2. We can make a really nice graph of our a of x function. And there it is, right over our interval, okay? And what we're doing is we're connecting. Check this out. From my 0, okay, my function's decreasing. I'm accumulating area at a decreasing rate. Well, check it out, because these are all, my slopes are positive, which is why I have positive slopes if you look at that from 0, but they're decreasing at a decreasing rate, which means there's my maximum, and then I'm accumulating still negatively at an increasing negative rate, but I'm concave down, okay? Last one. Sheet. Okay, why do we want to do this one? Well, because we've done 2 lines, and now we're just going to try to ballpark a bit. So what we're going to do first is graph f of t. Graph this f of t. Well, when I look at that little f of t, you know, I like to shortcut things, and I'm going to say that's t times t minus 2. So I'm going to say I have an x-intercept at 0. and x-intercept here at 0, and I got one at 2. Hey, that means my vertex is going to be there at 1, and when I plug a 1 in there, I get 1 minus 2, so I get a negative 1. And then when I'm over here at negative 1, I get, what, 1 plus 2, I should be getting 3. And then when I'm at negative 2, I get negative 2 squared is 4, minus 2 times negative 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. That puts me all the way up to there. And I got to get my 3 yet. Well, that's going to be 9 minus 6, right? 9 minus 6 should give me 1, 2, 3. Oh, check it out. It's symmetry. So here is my accumulator. Okay, so this is little f of t. Okay, or it's actually little f, it's f of t, but it's also the same as little f with x in it, which actually equals the derivative of my area function. Here's a huge connection right here. The fundamental theorem, part 1, the derivative of the area function is little f with x in it, okay? So, what is the antiderivative? We know what this is going to be. What picture should be down here? It should be some type of cubic, shouldn't it? And also, if I have a 0 and a 0, should I or should I not have at least 2 flattenings in there for zeros, okay? So, let's get this. Well, where are we going to start? We're going to say our x and our a of x, we're going to start at our bottom number, which means we want to find a of negative 1 is the integral negative 1 to negative 1 of f of t dt. So when we put a negative 1 in there, we're going to get a 0 out because that equals 0. So I'm going to say negative 1, 0. And now I'm going to go right. Now we're going to have to estimate here, because now I'm finding a of 0 is my integral from negative 1 to 0 of f of t dt. Okay, so we're going to say 0. But now it's not lines, now it's a curve, okay? And I need to be able to pick. Oh, what did you not put in there, Kruger? You didn't put your area accumulator line in there at negative 1. There he is. Okay, woo. There's my area accumulator line. And if I had to ballpark how much is right here, okay, well, if I made this into a triangle, I can see the area that's going to be underneath here. It's a little bit less than half of those 3 boxes, right? Which would be, I would think, but I'm going to call it, it's about 1.5 or 3 halves. I'm just going to ballpark it at that. And I know it's a little bit less than that, but it's a little less than 1.5. So when I plot it, maybe I'll go a little bit less, but I'll be happy. And then I'm going to find a of 1. Well, that's my integral from negative 1 to 1 of f of t dt. What does that equal? Well, that's going to be my 1.5 plus, now I'm accumulating more. Well, now I'm accumulating this. Well, I don't know. I would call it about a half-ish maybe, or 3/4. It's about 3/4 maybe. I don't know. What do you want to call that? Negative 1 to 1? Maybe plus negative 0.75. So probably going to be a little bit more than 0 somewhere in there. I'm just going to ballpark him in there. I don't know if I am at or below. I don't know exactly how much is here. It's I don't know exactly how much is there. Those two could potentially. Well, they couldn't wipe each other out. Well, they could. You never know how steep or concavity it is. So we're just going to say that. I'm going to throw it right around. What would that be? About 0.75-ish, somewhere like that. Okay. And it's okay. We're ballparking. There's no way for us to get the exact under the curve because it's not a line. And we're going to find a of 2. Well, that's going to be negative 1 to 2 of f of t dt. And if I keep going with where I was at 0.75 plus how much more? Ooh, I'm going to say that's about another negative 0.75 if I had to, right? We're just going to say we're approximately, I don't know if I'm above or below. I could be positive, I could be negative. I don't know exactly what it is. I'm just ballparking it here. And so we're going to say 3. And when you do this on the AP, they're not going to give you hard ones like this. This is just extension here, -1 to 3 of f of t dt. Well, that's going to, it didn't really need that little parenthesis there. That's okay. But didn't want to do that. That's going to give me about my 0 plus. Now what am I accumulating here? Well, now 1, 2, 3. Now I'm accumulating this, and I'm kind of thinking that's about back to my 1.5 if I had to call that. So 1 1/2. So I'm going to throw this back 3 at about 1.5-ish. And I'm going to throw this back up around in here with my calibration. So I still got to go left yet, don't I? And I'm seeing everything I need to see in here. I still need to go left. Okay, so now when I go left, I need my a of -1. No. Yeah, -2, excuse me. -2. We already found -1. So that's going to be -1 to -2 of f of t dt. Well, that's going to equal my starting at 0. And now I need to think, well, now I'm going left. Okay, so now I'm accumulating, holy smokerinos, roughly 1, 2, 3 plus. And what I would do is I just try to break this into a triangle, which I'm probably going to be under that, but that's 1, 2, 3, 4, 5 high by 1, so that'd be like 5 halves. I'd have to add that. So that's like -5.5 for all of this in there, wouldn't it roughly be? Because as I'm accumulating my area, these guys are positive, but because I'm going left, those are negative. So I would say, roughly speaking, I'd be at -2 or -5.5-ish. And that's going to put me somewhere down here. Well, what is that going to make that guy look like? Kind of like that, which hopefully makes a little bit of sense to you, because if this is truly little f of x, remember that's the derivative of a of x, which means I have a flattening and I have a flattening. I have a flattening and I have a flattening. My area accumulator line starts at 0 for my particular rate. I can see here I'm decreasing at a decreasing rate, right? Right there, I'm decreasing at a decreasing rate of area, concave down, still decreasing, but I am now changing things around there a little bit, right? So let's keep on a trucking. Why do we need to know how to do this? Well, I'm going to let you answer these questions here, okay? Answer the following questions about the relationship between f of t and a of x, okay? What is the value of a? Well, that's saying what is the value from the integral from a to a of f of t dt. That's my area accumulating line, and that's always going to be 0, okay? What did you notice? A maximum or minimum of a? A maximum or minimum of a is a what of f? Well, what was that? A maximum or a minimum of a, because this is my a of x function, is a what of f? And they're zeros, right? They are, is a 0 of that. And a point of inflection, if I come back here, check it out, I have concave down, I have concave up. I have a point of inflection in here. Where is that point of inflection going to occur? Probably right there at the minimum or maximum, okay, of F. Where at a max, ooh, that's too many M's. Max/min of F. Now we learned all of this. This part, accumulating area, is new. This is not new at all. Okay, none of that's new. And like when I reviewed before in the beginning, none of that was new either. What are you talking about? Well, if A prime is positive, we know A is increasing, right? And if A prime is negative, we know A is decreasing. And we know if A prime is greater than 0, meaning A prime is increasing, what do we know? We know A double prime is positive or greater than 0, and if it's positive, it's concave up. And we know if A prime is less than 0, meaning the derivative of A prime is less than 0, okay, then we are concave down because an A double prime would be negative, right? Or I guess I'm going to say increasing. If A prime is greater than 0, meaning it's increasing, meaning it's decreasing, not the value. So I guess I better justify that appropriately. A prime is increasing or is increasing. So if A prime is increasing, I know A double prime is positive, implying A is concave up. If A prime is decreasing, well, that implies A double prime is negative, which implies A is concave down. Okay, and we're going to use all that good stuff. How are we going to use that? Well, if you want to try these 4 problems before tomorrow, I highly encourage you to try them. But the big connection here is the graph of a differentiable function f. Hey, this is f. That's f. What is f? F actually equals h prime of x, because this is a function defined as an integral, which means if I take the derivative of this, that's how I get little f out, right? So find h of 1. Find h of 1. Well, that's a hard one. H of 1, well, that's my integral from 1 to 1 of f of t dt. What's that? It's 0. What the heck is h prime of 4? I don't know. What is h prime of 4? H prime of 4, well, wouldn't that mean h prime of 4, wouldn't that equal f of little f of 4? Wouldn't it equal little f of 4? Because if I took the derivative, if h of x equaled the integral from 1 to x of f of t dt, remember, we just spent a while doing this, and I took the derivative of this. That's h prime of x. This is the derivative of the antiderivative. That gives me a little f of x out. So h prime of 4 has to equal f of 4. F of 4 equals 2. Therefore, h prime of 4 equals 2. Okay? And we'll continue from there tomorrow, and I'll finish up the rest of these problems. But other than that, have a great day. Thanks for playing math. Good night.